This session is about the electromagnetic spectrum, which is in paper 2, and it's for combined and triple scientists. Electromagnetic waves are transverse waves that transfer energy from place to place, and they all travel at the same speed in a vacuum or air, which is 300 million meters per second. They're made up of vibrating electric and magnetic fields that act at right angles to each other. You have to know the order of the electromagnetic spectrum. It starts with radio waves, then microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. If you look at radio waves, they are long wavelength. Some of them are bigger than the Earth. They have a low energy and low frequency. At the other end, gamma rays are very short wavelengths with high energy and high frequency. Radio waves. These are the low frequency, long wavelength waves. They're used for communication such as radio and television. What happens is an oscillation in an electrical circuit, sort of like an alternating current, sets up an electric field that moves out from that wire. This is the aerial that produces the radio waves. The electric and associated magnetic field travel out from the aerial, and they might reach the aerial on a radio. And as the electric and magnetic fields go past this, it produces an alternating current in the aerial, so it detects the radio wave. So you need to learn that they are produced by oscillations in electrical circuits, and they're also detected as they induce oscillations in an aerial. So when radio waves are absorbed, they create an alternating current with the same frequency as the radio wave itself. Microwaves. Microwaves are used for satellite communication and for cooking food. Infrared is used for electrical heaters, also for cooking food, but make sure you're careful to specify that this is ovens and grills, and for infrared cameras, which are used for night vision. We looked quite a lot at absorbing and emitting infrared, and the amount of infrared that's given out or taken in depends on the temperature of the object compared to its surroundings, the surface area of the object, and also the colour of the object. Remember, dull dark surfaces are good absorbers and good emitters, and shiny light surfaces are poor absorbers and poor emitters. There is also a required practical on infrared, which used Leslie's cube, and there's a separate video to watch to go through this. It had different colour surfaces, and we made sure that the infrared detector was a fixed distance from each surface and measured the amount of radiation coming off. The surface area of each side was kept the same. This was a control variable, and the temperature of the surface had to be the same because the water was poured inside the cube. Visible light, going from red at the longest wavelength to violet at the shortest wavelength. Red, orange, yellow, green, blue, indigo, violet. Visible light is used in optical fibres. Remember, it bounces along the fibre with total internal reflection at each of the surfaces. Ultraviolet is used in energy-efficient lamps and sun tanning. In the energy-efficient lamp, the glass tube contains a layer of phosphor that produces light when it's activated by ultraviolet rays. These are given off from the argon-mercury mix inside it when it's exposed to an electrical current. But ultraviolet can cause skin to age prematurely and also increases the risk of skin cancer. X-rays and gamma rays are the high frequency and short wavelength rays right at the end of the electromagnetic spectrum. They're used in medical imaging and also cancer treatment. X-rays and gamma rays are both ionizing radiation that can cause the mutation of genes and so cause cancer. Gamma rays originate from changes in the nucleus of an atom, and we've learnt about them in the radioactivity topic as well. X-rays are absorbed by bone but pass through soft tissue, which allows us to produce images of the body. Ultraviolet waves, X-rays and gamma rays all have hazardous effects on the human body. And the effects depends on the type of radiation and the size of the dose. Radiation dose is measured in sieverts. It measures a risk of harm resulting from an exposure of the body to the radiation. You don't need to remember sieverts, but they might use them in an exam question. And remember, 1000 millisieverts is equal to 1 sievert.